Welcome back. Now, this time we'll be looking at Charles' law. In our previous video, we looked at Boyle's law and some calculations involving Boyle's law. So now we'll consider Charles' law alongside with Dalton's law of partial pressure and Gay-Lussac's law of combining volumes. Now, looking at Charles' law. Now, this law was postulated by a scientist named Jacques Charles. And what did this law state? Now, the law states that the volume of a given or fixed mass of gas is directly proportional to its temperature, provided the pressure remains constant. So what does that mean? It means that in Charles' law, the two quantities that are of utmost relevance are volume and temperature. So we don't need pressure because pressure is supposed to be kept constant in Charles' law. So it means that there is a direct relationship from the mathematical expression. Now, the mathematical expression or representation is given by now volume of a given or fixed mass of gas is directly proportional to what? To the temperature. And of course, by the introduction of a constant, it becomes V equal to KT. And if you want to make K to be subject to formula, then it becomes K is equal to V over T by division of both sides by T. And that gives you this. So relating more than one gas, you'll be having V1 over T1 equal to V2 over T2. So that is actually the formula for finding Charles' law. Then again, if you want to use a mathematical representation or graphical representation of it, you can be having volume as against temperature, and then it goes like this. And what does that mean? It means an increase in volume results in an increase in temperature, just like 1, 2, 3, 4 here. 1, 2, 3, 4. So if I drag it to this point and I hit this point, that's 1, 1. If I drag it to this point, I hit it there, that's 2, just like that. So when you increase volume, you are invariably increasing temperature, or when you increase temperature, it tends to increase volume. Then let's see some questions on Charles' law. Just one question we do. So let's see a question on that. On the board, we are having a question on Charles' law. And looking at this question, it's a bit lengthy, but you don't need to stress yourself over it. Why? Because it seems to be lengthy, but then again, it is very easy for you to attempt. Just follow suit. Now, look at this. Alex is playing outside with his ball filled with air of volume 0.75 dm cube at a temperature of 27 degrees Celsius and 0.9 atm pressure. What would be the volume of air in his balloon if he puts it in a pot at a temperature of 75 degrees Celsius, provided that the pressure remains constant? So this is common with so many students that whenever they are given questions in gas laws, they will just start representing their parameters. But let me tell you this, before you represent your parameters, ensure that you have concluded with the reading of the question. Why? Because sometimes they might introduce quantities that are not even needed at the initial step of the question, and then at the end it will not be revealed or exposed that they are not needed in the question. Okay, look at this. You know you were given 0.9 atm pressure initially, but at the final end we are told that provided that the pressure remains constant, meaning the pressure is not even relevant. And you know that in Charles' law, pressure is what? Is kept constant. So it's obvious that we are using Charles' law in this case. Alright? So we don't need the pressure even when we are giving pressure in the question. Alright? So what's the formula? The formula of Charles' law is V1 over T1 equal to V2 over T2. So let's represent the parameters. Looking at this, we are giving the initial volume being V1. V1 is 0.75 dm cube. Then while the temperature, the initial temperature now, T1 is equal to 27 degrees Celsius. Then we were told what would be the volume of air. So we are told to calculate volume V2. We don't know. Then while that of the T2, the temperature 2 is 75 degrees Celsius. And this is very important that you pay attention. Whenever you are giving temperature in degrees Celsius, you must convert to Kelvin being the absolute temperature. I explained that in the previous video. Now, looking at this, if you want to convert Celsius to Kelvin, don't forget you add 273 to the value, and this becomes 27 plus 273, and this gives you 300 Kelvin. Then while this one, we have to convert again 75 plus 273, and this gives us 348 Kelvin. All right. So then let's plunge all these parameters into the formula, which is this one. So it becomes V1. Our V1 is 0.75 over, then T1, we are now going to work with that 300 equal to, then V2 is now unknown, then while our T2 is 348. So when we cross multiply, then it becomes 300 V2 equal to 0.75 times 348. So our V2 would be equal to 0.75 times 348 over 300. So V2 would be, let's use our calculator for that. That becomes 0.75 times 348, then divided by 300. So this gives us 0.87 dm cube. So that's our answer. Now, it's very logical to conclude that initially we were having 0.75, and then the temperature was 27. Now, finally, we are having temperature to be 75, an increase in temperature. So we are supposed to be expecting an increase in volume, and we had it, which is 0.87, bigger than the previous volume, 0.75. So that's a question on Charles' law. So the next that we are about looking at will be on the Dalton's law of partial pressure. Now, considering the Dalton's law of partial pressure, this law was actually postulated by an English scientist named John Dalton. And what does this law state? This law states that when there is a mixture of gases that do not react chemically together, the total pressure of the gases would be the sum of the individual partial pressure of each of the gases in the mixture. All right? And one thing that you need to know about this Dalton's law of partial pressure is that there are relevant formula that will be of help to you, especially for the calculations. All right? Just like you can picture it this way, that if you are having, let's say, the pressure of, let's say, gas A to be 3 atm, the pressure of gas B to be 4 atm, and the pressure of gas C to be 5 atm, something like this. Now, when you now have, let's say, in this container, you are having A, B, and C. Now, the total pressure that will be generated in this container would be as a result of the sum of their individual partial pressure. So it means that the total pressure would now be 3 plus 4 plus 5. And of course, this gives us what? 12. So it means the total pressure generated by these gases is actually what? 12. So that's just the Dalton's law of partial pressure. Now let me give you a relevant formula that will be of help to you in terms of calculations. Now, PT, which is total pressure, is equal to the partial pressure of gas A plus partial pressure of gas B plus partial pressure of gas C. Is a continuous law. It all depends on the number of gases that you have in the mixture. All right. So this formula is still very important. Key formula. Then there's still another key formula. Now, what about a situation whereby you are told to calculate the partial pressure of a particular gas in the mixture? So how do you do it? So now, if you are told to calculate the partial pressure of, let's say, gas A in this mixture, partial pressure of gas A, what you do is this: you obtain the mole fraction of gas A, mole fraction, I'm going to explain this, of gas A, then times the total pressure of the gases. All right. So how do you now get a mole fraction of a given gas? Now, mole fraction of, let's say, gas A now, gas A is given by the number of moles of gas A over the sum of the number of moles of all the gases in the mixture. All right. So what this one means is that, let's say, for the mole fraction in a simplified pattern, the mole fraction of, let's say, gas A. Let's say you have three gases A, B, and C. So what you do is this: to get the mole fraction, it becomes the number of moles of gas A over, then you now have the number of mole of A plus number of moles of B plus number of moles of C. So that's what it means. That's just the implication. All right. So if you know these three formulas, then you can attempt questions on Dalton's law of partial pressure. So we are going to look at questions on Dalton's law of partial pressure applying this formula. All right. So let's look at a question or questions on Dalton's law of partial pressure. On the board, we are having two questions on Dalton's law of partial pressure. Question 1. A gaseous mixture contains 5 moles of helium, 3 moles of argon, and 2 moles of nitrogen. What is the partial pressure of nitrogen if the total pressure is 15 atmosphere? So the question is, what is the partial pressure of what? Nitrogen. And don't forget that the partial pressure of any gas is given to be one of those formula I gave. Partial pressure of gas A that I gave was the mole fraction of gas A times the total pressure of the gas. All right. So in this case, we are told to find the partial pressure of what? Nitrogen, and we are having other gases as well. So what do we do? Let's get the mole fraction of nitrogen first. You know, this gas A now is just like nitrogen gas and nitrogen gas. You get the point now? So now, what are we supposed to do? Let's get the mole fraction. So the mole fraction of N2 becomes the number of moles of N2. Remember that the number of moles of N2 over the moles of N2 plus moles of helium, He, plus moles of, then the last, argon, Ar. So when we do that, it becomes the number of moles of nitrogen is given to be 2 moles of nitrogen now. So 2 over, then 2, which is still the same as nitrogen. Then for helium is 5. So 5 plus, then the moles of this one is 3. That's argon. So when we do that, it becomes 2 over, this is 7, this is 10. And that's 1 over 5. That's if you reduce. Then now we know the mole fraction. Then what about the total pressure? We are given as to be 15. So we can easily get our answer now. So it becomes partial pressure of nitrogen becomes 2 over 10 being the mole fraction times 15, which is the total pressure. And that becomes 2 times 15 is 30. So that will be 30 over 10. And the answer is 3 atm. All right. So that's the answer. So that's for question 1. So let's look at question 2. Question 2. Now looking at the second question, If the vapor pressure of water is 13 millimeters mercury, what is the partial pressure of oxygen gas collected over water at 760 millimeters mercury? Now, looking at this question, you get to know that the total pressure of the gas is given to be 760 millimeters mercury. All right, that's this one. Then we are given the vapor pressure. So the pressure of water vapor is given to be 13 millimeters mercury. All right. Now, what are we told to find? We are told to find the partial pressure of oxygen gas collected over water. So it means you should take cognizance of this. Gases that are collected over water, the pressure of any gas that is collected over water is the summation of the pressure of the gas itself, that's the partial pressure of the gas itself, and that of the water vapor pressure. All right. So let me just write it. Now, pressure of gases collected over water is equal to, we have the pressure of the gas itself, that's the partial pressure now, partial pressure of the gas plus the water vapor, the pressure of water vapor. All right. So in this case, now we are given the total pressure of the gas to be what? 760 millimeters mercury. So it means the partial pressure of the gas, the particular gas we are interested in having the partial pressure is actually oxygen. So that will be X, then plus the pressure of water vapor is 13. So that's 13. So you can easily get it. That becomes X is equal to 760. When you move the others to this one to the other side, it becomes minus 13. And that automatically becomes 760 minus 13. That's 747. So it's 747 millimeters mercury. So it's that easy. This one is straightforward than the other one. All right. So we are done with questions related to Dalton's law of partial pressure. I just want to be very brief, so you can use all these questions where I've just solved to attempt other questions that you have. Then let's quickly proceed to looking at the next, which is the last. We are done with this. So the last is Gay-Lussac's law of combining volumes. For the Gay-Lussac's law of combining volumes, it was postulated by a man. Gay-Lussac's law of combining volume volumes. This law was postulated by a man named Joseph Louis Gay-Lussac. And what does this law state? It states that when gases react, they do so in volumes which are in simple ratios to one another and to the volume of their products if gaseous, provided the temperature and other physical conditions are kept constant. All right. Now, looking at this law, it's a little bit complicated, but then again, I will explain it for you to be able to pull through. Now, it has to do with gases. Now, of course, you know, it's very difficult for you to obtain the mass of a gas. Why? Because of the rate of diffusion of gases. So most times, scientists, they work with the volumes of gases. So when you carry out reaction of gases, you must always represent with the simple whole number ratios of the volumes present. So it's just like you having hydrogen gas reacting with oxygen gas. Both of them, they are gases. Let's say to produce H2O gas, that's steam. Now, when you balance this reaction, how many hydrogen here is 2, 2. So for you to balance it, here should be 2 and here 2. So everything is balanced. That's 4, 4, then 2, 2. But in terms of the ratios, this is actually 2, 1, and 2. So 2 ratio, that's 2, ratio 1, ratio 2. All right. So in simple whole number ratios. So in this case, I can actually say that since I have a gaseous volume, that's the reason why you are having the mole ratio to be represented. All right. So if your volume, the what's it called, the products are not in gaseous phase of matter, then they do not appear in Gay-Lussac's law. All right. So for you to understand this thing better, we'll look at questions. All those questions that pertains to you solving or calculating for the residual gases. I guess you must have seen questions like that before. So we are going to attempt a question on that, applying the principles of Gay-Lussac to better understand the principle. So let's see a question on Gay-Lussac's law. On the board, we are having a question on Gay-Lussac's law. And this question will guide us to, attempting other questions pertaining to Gay-Lussac's law. All right? So you just pay attention as I run through the series. Now, looking at this question, what is the volume of residual gases in a reaction involving 15 cm cube of methane and 40 cm cube of oxygen? In Gay-Lussac's law, you must know how to represent reactions, how to represent balanced reactions. Now, we are having two substances that would react, two gases, methane and what? Oxygen. And methane has a formula, CH4. Reacting with oxygen, it gives CO2 plus H2O. All right? So now, this is from the lessons of organic chemistry. You tend to understand how you can represent this kind of reaction. So methane happens to be a gas, oxygen is a gas, CO2 is a gas, then water is liquid. So the only liquid product that you have there is water. Then let's see whether the reaction is balanced. Of course, it's not balanced. We have one carbon here and one carbon balanced, but hydrogen here is 4, while over here is 2. So you have to make here 2, so that it comes 2 times 2, that's 4. Then now, for oxygen, oxygen here is 2, here is 2, then here 2. So total here is what? 4. So you have to make here 2. So everything is balanced now. All right? So what are the things that would make your work to be very simplified? By bringing out all the necessary, how would I put it now, parameters that you need to fill in. Look at it. Now, first, you need to know your mole ratios. Then you need to know the initial volumes of gases. Then you need to also know the reacting volume of gases. Then you also need to know the volume of gases after reaction. Then you also need to know the residual gas, which is the one you are told to calculate, the residual gases. All right. So these are the things that we need to know. So looking at the mole ratio, let's follow up. Now, what's the number of moles of methane here? Here is 1. Then while this one is 2. Then while this one is 1. Then while this is 2. So it's like 1:2:1:2. Then now, from the question, we can get the initial volumes of the gases that were provided. We are given the question that 15 cm cube of methane reacted with 40 cm cube of oxygen. So the initial volumes before the reaction, we have 15 cm cube of methane, and for oxygen is 40 cm cube of oxygen. Then it's obvious that we don't have any volume of CO2 produced. Remember that we are not going to have any business to do with water. Why? Because water is a liquid component here. And remember that the only time that you actually give credit to your product is only when it is in a gaseous phase of matter. So we don't have any business to do with water there. So do we have initial volume for CO2? No, because what we are giving the question was just the volume of methane and the volume of oxygen. All right, so we can write here 0 cm cube. We don't have any initial volume. Then we have attempted that. The next, the reacting volume of gas. Remember that it is both volumes that would now be reacting. But then again, observe 1:2, meaning look at this one, 15 cm cube of methane. If it reacts with twice of its volume in oxygen, it's going to be 30. So twice of 15 will be 30. So what methane needs is twice of oxygen that it needs in terms of its volume. So for it to react completely, remember that methane is 1, oxygen is 2, 1:2. So any volume of methane needs twice of that volume to completely react with oxygen. But then again, looking at the side of oxygen, oxygen is 40, which is under, if you check the balance reaction now, you have 2 here. So just like I assume that 2 of oxygen is having this volume of 40 cm3. So 2 of oxygen requires just 1 mole of methane to react completely. So if here is 2 that constitutes this volume now, so it means that 1 of methane of this one should be 20. So it means 40 cm3 of oxygen requires 20 cm3 of methane to completely react. But then again, the question, we are not having enough volumes of methane, so we can't go in the otherwise, but rather we'll go in this forward, in that 15 of methane requires 30 of oxygen. That's twice of its volume, being the mole ratios here. So it means that the one that will react here will be 15. The whole of the 15 will react, and it needs just 30, meaning twice of it, 30 cm3 of this oxygen to completely react. But mind you, looking at that CO2, are you aware that going by mole ratios, 1:2:1, so it means certainly 1 mole of methane will produce 1 mole of CO2. In terms of equivalence of volume, 15 cm3, which is the 1 mole of methane, will be equivalent to producing 15 cm3 of CO2. So we have gotten the reacting volumes here. Now, we'll look at the volume of gases after reaction. Of course, you know that this one will be completely reacted and there will be nothing left of the methane. So it means after the reaction here will be 0 cm3. Then after the reaction, what will be left of this gas will be 10 cm3. And of course, this one is still left with its 15 cm3 that was produced. Alright, so now how do you now get the residual gas? You simply add up the excess gas that was left plus the gaseous product in terms of its volume, and then that becomes residual gas. The gases that are now left in the medium becomes 10 cm3 plus 15 cm3, and that gives us what? 25 cm3. So is that easy? Is that easy? So the thing is that the secret of you understanding this concept very well is by rewatching the video. But mind you, let me just give you this tip. Now, always work with the gas with the lower volume to be your standard. Because if you check, I worked with the gas with the lower volume to be my standard, because now looking at this one, 15 cm3 of methane and 40 cm3 of oxygen. Now you can picture it this way using the mole ratio. 1 of methane is 15 cm3, 2 of methane will be what? 30. Then you see this one, what's it called? Oxygen. Oxygen is 40 here, 2 of it is 40, then 1 of it is what? Is 20. So from there you ought to know that the one that is actually smaller is what? The one of 15. Because 1 of this is 20, 2 of it is 40, then 1 of this is 15, then 2 of it is what? 30. So which one is smaller? It's actually this. So you use this as a standard. That's another tip. But then again, you can just work with this pattern and then you end up getting your right answer. So anything that you're not clear with concerning these gas laws that we've just seen, you can actually drop your comments on the comment section there, and then I'll be there to attempting replying your comments. All right. So it's my hope that you've been able to understand everything that I've just explained concerning the gas laws. We are still left with some other gas laws. But then again, we'll just stop the video here, and in our next video, we'll conclude with the other gas laws. All right. So it's my hope that you've understood it. Thanks for watching. If you like this video, just hit the like button and don't forget to subscribe. Share the video to your friends so that they'll be aware of the channel as well. Okay. Thanks for watching and God bless.